about 15 seconds here.
Okay.
Okay. Good afternoon. You've joined us on Likeable Science here on ThinkTech Hawaii. I'm your host, Ethan Allen. We're talking energy today, and a very exciting talk will be here. Joining me actually via phone today is Dr. Aaswath Raman from Stanford University. He is an amazing guy here. He got his, well, I should just say welcome, Aaswath.
Thanks for having me.
Glad you're able to join us here by phone. Yes, this is a picture of him up there now. Aaswath got his AB degree and MS from Harvard University in, I believe, in physics and astronomy, and went on and took a second master's and a PhD from Stanford. So he's got a lot of educational background. He's working in a lab there that's looking at nanophotonics. So maybe you could just start out, Aaswath, by telling us a little bit about what nanophotonics is really all about.
Sure. Nanophotonics really refers to the idea that if you can make objects that are really small and have patterns that are really small, and I'll explain how small it needs to be, they can interact with light in unusual ways. So in ways that you can't normally find in nature or with kind of natural materials. So the key aspect here is that we're able to kind of structure and maybe periodically pattern different kinds of patterns into materials on scales that are smaller than the wavelength of the light we want to affect. And it turns out through some physics and some interesting science that you can enable really cool and nifty things. So probably one of the coolest things that's come out of this field in the last decade, it's not necessarily practical, but it's certainly cool, is cloaking, sort of like Harry Potter's cloak of invisibility,
right.
And how you might actually be able to design materials that do that.
Right. There is this kind of nanostructuring in nature in terms of iridescence in bird feathers and that kind of thing, but you're talking about a human-controlled version of it to really even play sort of more interesting games with light, then really bending it around in very controlled ways, or in this case, changing its wavelength or frequency.
I think, for example, the example of iridescence, and even in some very old Roman and Greek urns, you find examples of behaviors that are fundamentally enabled by the fact that those materials interact with light at the nanoscale and do something unusual. And those things have certainly served as inspiration for scientists and engineers in now pushing forward to actually kind of actively control this behavior for our own purposes instead of maybe just relying on what nature has provided us with.
Exactly. That's the whole beauty of nanotechnology, in that it brings a whole new level of control of materials into the hands of scientists and engineers, and they can make materials do very interesting things and have so-called sort of emergent properties that you could not expect. Indeed, I used to, when I was at the University of Washington Center for Nanotechnology, I did a little very simple public demonstration that we would let children do, where to take a drop of clear nail polish, drop it on water, and then pick the film up on a piece of black paper. And the film was iridescent. And the iridescence came from essentially the drop had thinned out to very close to nanoscale dimensions. And you could actually see the changing color patterns on it. So a very simple way of showing the same kind of nanoscaling that you're talking about.
Yeah, definitely. And another way to look at it is probably, the back of a CD or DVD. even though that's becoming less common these days. If you look at the back of it, you see kind of light, you can see a spectrum of light come out of it, and part of that is due to the patterns being so tightly packed on them.
Exactly, exactly. There's an amazing density. Our audience, perhaps we ought to clarify that the scale that we're talking about, we're talking on the order of a few nanometers, and the definition of a nanometer that I always liked and found very meaningful, that a nanometer is just about the amount that your fingernails will grow in 1 second. So.
I don't think I've heard that one before, but I like it.
Yeah, it's a good one. It makes, people, everyone understands their fingernails grow, but they know they don't grow much in a second. But so it's a billionth of a meter is what it is, right?
Yes, that's correct.
Right. So let's talk a little bit though about this recent. You had an article that's just appeared or is just appearing in Nature now about this really amazing sort of mirror that you've developed.
Sure. It's basically a surface, and like you said, when you look at it, it looks like just a really nice mirror. But when you leave it outside in the daylight, exposed to the sun, even pointed at the sun, it will actually stay naturally at a temperature below air temperature.
Wow.
So this is, if you think about it, pretty counterintuitive to our everyday experience.
Right.
Normally, we think of objects when they're under sunlight, they'll heat up.
Right.
So if it's asphalt or whatever, it's going to warm up pretty quickly. And normally we think of when we bring objects into the shade that they'll actually cool down. This surface, I'll explain why later on, but this surface actually, by its properties, will when I bring it into the shade, will actually warm up a little. And will cool down when it's outside. Now, the most important thing to know about this kind of surface is the reason this effect works is that it's exposed to the sky. And it's less about the sun than you might expect.
So it really works, you're saying, if it's outside, because you're in essence radiating, as I understand it, and please correct me if I'm wrong here, but it radiates any incoming heat that it's picked up, reflects it back basically at a particular wavelength or frequency that passes very well through our atmosphere, and so it ends up basically out in the cosmos.
Actually, it's slightly different from that. The main thing it's doing is it's actually radiating its own internal heat. So any heat that's really being conducted to it. So the way to think about this is, any object that's at a certain temperature emits or radiates its heat out as a form of light. For us, at typical Earth temperatures, that light is in the form of infrared light.
Right.
So this is, for example, how infrared cameras work, or thermal imaging cameras at least work. They're detecting the light we all give out, and it's the kind of light we can't see. And so what this kind of surface is doing what all surfaces do, which is it's radiating its heat out as a form of light, but it radiates more out than it gets back from both the atmosphere and the sky. And to understand the real kind of, I guess, the deeper science here, the way to think about this is that, and this is kind of a fun fact, that on a clear night, almost any surface exposed to the sky will naturally be at a temperature below air temperature.
That seems odd.
Yeah, and this is something we've known about actually for a while. It's the basic reason for it is the fact that while a lot of the heat that gets sent out is infrared light I mentioned earlier,
right.
A lot of the heat that gets sent out as infrared light is absorbed by the atmosphere and sent back to you, kind of reflected back. Some percentage of it is actually able to completely escape and go into space and into the cosmos, as you said. And this concept is called radiative cooling.
Right.
The last 100 years, I think people have sort of understood this concept, and it's been a very important part of how we actually understand things like climate change.
Mm-hmm. Right. It has to do with the balance of sort of energy in and energy out.
Right. So it's basically something that just happened. You can think of it, if you think about the sun and solar cells and solar energy, until maybe about 50 or 100 years ago, we really didn't try to exploit the fact that it was heating up objects everywhere. There were certainly cultures and civilizations that tried various things, but not on a large systemic scale. And there was a ton of energy that's coming down onto the surface of the Earth from the sun at any given point in time during the day.
Right.
And the choice we made was we should actually find a way of actively exploiting it and using this to power our energy needs. And in a similar way, what I guess I'm trying to argue here is that this is something that happens right now at night all the time. And starting maybe in the 60s and 70s, a handful of scientists and engineers actually thought, hey, maybe we should also, like we're doing with the sun, maybe we should try and exploit this effect as well for our own energy needs in some way, instead of just letting it happen.
Right, right. This is very interesting. I'll tell you what, we're going to jump out and take a brief break here, and then we're going to really dig into this when we come back. I'm here on Likeable Science. I'm your host, Ethan Allen, talking with Dr. Aaswath Raman from Stanford University. We'll be right back.
Aloha, this is Martin Despang, co-host of the Urban Transcendence Show by Alejandra Yamashita and Martin Despang. And me being an architect and an educator in architecture, I'm really interested in that we make our urban environment here in downtown Honolulu as exciting, invigorating, and challengingly beautiful as our wonderful paradise natural environment. We're going to bring in guests from a diversity of areas that help us to learn how we can achieve that goal that shouldn't be that hard to reach. So we look very much forward to see you then. Thank you.
And you're back here on Likeable Science. I'm Ethan Allen, your host on Likeable Science here in ThinkTech Hawaii. And with me today via phone is Dr. Aaswath Raman from Stanford University. We're talking about nanophotonics, and more specifically about a rather amazing recent development that he has been the key leader of, developing a sort of a mirror that is made of nanoscale structured layers of materials that, according to him, actually radiates more heat away from it than it possesses or than it takes in, I guess. So tell us a little more about the mechanism of this, if you would please.
Sure. So, the motivation to actually do this came from the fact that while it's been shown now for decades that this kind of cooling effect can be attained at night, as far as we know, it hadn't been demonstrated during the day. And we were interested in figuring out how you could do this during the day. So the only real challenge to accomplishing this kind of cooling during the day is you need to simultaneously radiate your heat out very effectively, like surfaces do at night, and most materials do at night, but at the same time, you need to be able to reflect almost all the sunlight that's incident on you. And it's this combination of factors that enables this cooling effect then to be enabled and persist during the day when you're out under, say, the hot sun. So from the nano point of view, then, what's kind of cool is that you can, and no pun intended there, what's kind of neat is basically by making certain choices of material and by determining their thicknesses, you can kind of rationally and in a deterministic way figure out how this new kind of composite, multi-layered material will interact with light at different wavelengths. And I guess that's a good start to explain what it does.
So you and your colleagues experimented with this, I'm sure, over some time, and probably tried different combinations, different thicknesses, maybe different materials, and then have settled on a combination that works very well for essentially sunlight, skylight, more or less, in terms of the energy coming in off of those sources.
Yeah. It's actually nowadays you can you can actually do most of your playing around with different systems on a computer. So we're able to model these systems to a very high degree of accuracy. So we can just simulate, tens or hundreds of different structures and try and actually optimize for a particular design. And so the particular design we have, as you said, that we kind of arrived at after this kind of computer-based optimization process is one that is a very good reflector of sunlight and the infrared light the atmosphere sends back to you and that heats you up. But at the same time, it's able to efficiently radiate its heat out where the atmosphere is most transparent to infrared light.
Okay, so can we dig a little deeper into that? So just how does it radiate? So what is it that's making it radiate out so efficiently? I mean, I understand that certain wavelengths pass through the atmosphere very well, but how do you control that?
So you control that in the same way you control how it's able to reflect light, it turns out. It's just a slightly different target you're aiming for. It's more a function of how well it's able to emit and absorb light. So there's a very fundamental physical law, and this is getting a bit technical, but it's kind of helpful to understand. It's a law that says that emitting light, that is radiating light, is equivalent to absorbing light. So at a particular frequency or at a particular wavelength, if your object can absorb light, a certain amount of light for a certain amount of thickness, it can equivalently emit the same amount of light for that thickness.
Okay.
Now what that means then is what makes this kind of structure efficiently emit light where the atmosphere is transparent is the fact that we chose a couple of materials. One is called hafnium dioxide, the other is called silicon dioxide. And silicon dioxide, by the way, is just, it's everywhere. It's basically glass, it's part of sand. It's a kind of a universal compound we encounter everywhere in our daily lives. By kind of structuring their thicknesses and their layers and putting them in these alternating layers, and again, more importantly, by making sure those thicknesses are much smaller than the wavelength of infrared light, they actually are able to preferentially absorb and therefore emit infrared light at particular sets of wavelengths and frequencies.
Okay.
What that means is basically you can design a structure by putting alternating layers of a couple of different materials, and I'll explain what the key feature of having them alternating enables. By having them doing these kind of alternating layers, and by picking the thicknesses right, and by making sure you chose certain kinds of materials you can find in nature, you can have them interact with light and therefore absorb and emit light in ways that are not commonly possible. So it's really kind of a design-based approach to radiating and absorbing light.
Yeah, that's sort of stunning in its seemingly in its simplicity. I'm sure it's an incredibly complex design process. So it sounds like this you said you did a lot of your experiments were really essentially simulations that you did on computers, plugging in the parameters for different kinds of materials, different thicknesses, different numbers of layers, that kind of thing.
Yeah, exactly.
Super. So then you had confidence once you found the proper solution on the computer that worked, that when made the stuff up in the lab, and it actually played out the way you your prediction called for, right?
Yeah, it's never going to be exactly the same, but it's pretty close, and it's close, and it's close enough that we get the effect we were hoping.
Yeah, that's really outstanding, and I think the real power beauty of this here is what its potentials are, because some huge percentage, something 15% of the energy used in buildings typically are used to cool them, right? And if you can essentially take a big chunk out of that.
Yeah, I think that definitely was a part of our excitement and our interest in working on this kind of idea. Cooling is definitely a big part of energy use, and it also happens to coincide with with peak energy use in a lot of regions. So it's a major driver of peak demand. It's also, looking more globally, one of the more kind of interesting and potentially worrying trends is that more and more of the world is getting air conditioning.
Mm-hmm.
Global air conditioning use is projected to grow something like tenfold from today to the year 2050.
Wow.
And most of that is going to come from the developing world.
Mm-hmm.
Who can blame them? Because air conditioning certainly makes our lives much more comfortable and pleasant, especially in extremely hot conditions, and
right.
enables comfort and productivity. And it's something that's really it's an amazing technology. It's definitely revolutionized our lives, and it's also a big part, therefore, of the energy challenge we face going forward. So, when we think about the kind of technology we're working on, it's inherently something you will need a lot of surface area for. So it scales with area in a way sort of similar to solar cells.
Mm-hmm.
So you might imagine that for this to be useful, you would have to cover some significant fraction of a building's roof. And if it's a relatively short building, that means it's not super dense in its cooling needs per unit of the building's footprint. I think you can definitely tackle a huge fraction of its cooling load, depending on how you design the system. And that's pretty exciting because it's an entirely passive approach to doing that. There's no electricity input needed.
Yeah, that's the sort of mind-boggling thing about this is that it almost seems like you're doing some end run around a natural law, because you're dumping out more energy than is coming in a sense, and it sounds like a cheat,
Well, I promise we're not violating any physical laws. The way I look at it is, this is something nature, it's a property of how the Earth works as a whole.
Mm-hmm.
At night, the Earth as a whole cools by radiating part of its heat out entirely to space.
Mm-hmm.
It's more a question of, instead of just letting it happen, in the soil, in our roots, whether we can actually actively optimize for and exploit it, and in particular, optimize and exploit it during the day.
Right.
And at the end of the day, the trick to making this work during the day is to allow this cooling effect to exist while simultaneously reflecting all the sunlight that would normally completely wash out the effect. And then that gets exciting because, it's in the middle of the day when cooling needs are the greatest.
Right, and that's what you were talking about, that sort of 1-2 punch about having an extremely efficient mirror combined with this highly efficient radiator, basically, and being able to take advantage of both effects locked together in this, sort of a passive material, as it were. So it's not chewing up electricity, it's not using water, there aren't moving parts. It's a mind-boggling concept. We living here in Hawaii are very interested in that. We're very concerned about heat. We've actually gone through quite a hot summer here, and Lots of people are using lots more air conditioning than they usually do, and boy, hearing about something like what you have going there sounds like a great potential boon to Hawaii, because we're chronically short of, we have very expensive energy here. Our electricity is quite pricey because it's essentially all produced from fossil fuels. So again, this technology is just seems like a tremendous potential asset to our little tropical islands here.
Yeah, I think it's there's obviously a lot more work to be done to get this to be a practical reality, but I think where you'll find use is in places where energy is already really expensive and it can kind of compete just on a cost basis quite effectively, and in places where there's a need for air conditioning over a large part of the year and over a large part of the day. So obviously warmer regions, arid, dry regions also are, desert-like conditions. There's a kind of range of potential climates where I think that this will probably find its first use.
Excellent. And I want to, when we come back, I want to talk about sort of that use, how you see it being applied, where you see it being applied, when you see it being applied. But we're going to take a short break before that. Again, this is Ethan Allen here, and I've been talking with Aaswath Raman from Stanford University about nanophotonics and about his new photonic radiative cooling system. We'll be right back.
Aloha, I'm Hunter Hevelin, host of Sustainable Hawaii here at ThinkTech Hawaii. You can tune in every week on Thursday at 2 p.m. to see interviews with sustainability professionals from around the state and even further abroad, learning about activities with water management, food security, waste management, and a whole host of other fascinating opportunities to get engaged with making a greener island. So if you're interested in making the transition from consuming individuals to communities of producers, check us out every Thursday. Aloha.
And you're back here on Likeable Science. I'm your host, Ethan Allen, broadcasting here from the ThinkTech studios in Pioneer Plaza. Today, I'm talking with Dr. Aaswath Raman from Stanford University. We're talking about his amazing photonic radiative cooling system. This is a nanoscale structured material that passively radiates heat away extremely efficiently while reflecting sunlight with high efficiency too, and therefore actually being an effective cooling system. Now you've got this up and going. You've got as at least in the article I read, a pizza-sized reflector at this point, and the question comes sort of about scaling this up. How do you make this usable? What are going to be the next steps? What do you see as the upcoming barriers?
So for us, the key question is what's the best way of actually making use of the surface like this? So one possibility is, of course, just putting it on a roof as some kind of trim material. But there, I think the use is potentially limited, and it's probably difficult to make an economic case for it in most scenarios, because something like a conventional light roof, kind of cool roof, traditional cool roof system is already so very good, and it is also extremely durable. I think what's different and distinguishing about this kind of system is that it can go below the air temperature. So it can do better than just, so for example, if you were to, cool your building just by drawing in outside air, the best you could do is cool it to the air temperature that's outside.
Right.
What this enables by going below air temperatures provides you an electricity-free source of below air temperature cooling. And I think that gives us the opportunity to think about this in a slightly different way. And it's something people have thought about before in the nighttime version of this system, kind of a nighttime radiative cooling, which is that maybe the goal here is to instead kind of modularize it. So maybe package it in some way such that you can then not think of it as a roofing material, but so much as an actual module or system that you just happen to have on the roof because that's where it'll work the best. But it then is able to actually actively pump out heat from the interior of the building by plugging into the building's cooling system or to an air conditioner or a chiller. Mm-hmm. And so that's the direction we're taking with it, and where we think there could be a very compelling value for this. Now, I think what's at least hard for us right now, and something we're working on, is figuring out how to do that best. What's the best way of actually getting this to interact with or work with existing cooling technologies in an efficient way, such that it might make them more efficient or make them use less energy. And maybe in some scenarios, this alone can serve as a cooling system as well. So, and beyond cooling, we've thought about, what about, someday maybe even refrigeration. Maybe this can make refrigeration more intensive. Mm-hmm. And that's, of course, interesting in kind of off-grid situation.
Right. So, what about the issue, and I don't know, have you tested it, is this stuff durable? I mean, is it going to hold up over, weeks, months, years, being blasted by tropical sunlight, day in and day out?
Yeah, that's definitely a good question. The materials we have right now are reasonably durable, but I certainly would not imagine leaving it outside unprotected. I think that the way we're thinking about this is that you might imagine that this is just the core component of a larger system that encloses and protects this from the environment and kind of being outdoors in general. But so there's definitely a way of thinking about this where the actual core material here need not be itself exposed to the elements, but the larger question is how you actually construct an efficient and durable enclosure for this kind of system that simultaneously allows you to take specific heat loads that you wanted to get rid of and pass them through the radiating surface itself. So that's an open opportunity, something we're certainly thinking a lot about now, and I imagine other people have thought about this as well in the context of nighttime systems. But
right, because you can see this as having a lot of applications, both in sort of developed areas currently using a lot of air conditioning, big cities and all here in Hawaii, but also then in relatively remote areas too, where as you point out, electricity is expensive, unavailable, unreliable. Perhaps there might be several incarnations or several different kinds of systems you end up developing to use it effectively in multiple environments then.
Definitely. So, one way to think about this is that this effect already works at night, and there are handfuls of example buildings all over the world that actually make use of this effect at night by either cooling a tank of water or spraying water down over a cooling surface and then collecting that chilled water for use during the day. So I think there already sort of are examples of how you can use this at night, and you can kind of build off of that. But it's compared to the potential, I think there's been relatively little investigation of this compared to, say, for example, the amount of research that is done into solar cells or solar thermal technologies. And when you look at the history of photovoltaics or solar thermal, you'll see that in many cases, where they were adopted first were places that were energy scarce for whatever reason. And that's because energy is expensive to begin with. And in a similar way, I think this kind of technology has the opportunity to make a big impact in places where energy is expensive, just because it provides, it just has a very compelling kind of value proposition to people that are living there, that this, will probably the break-even cost for it can be much lower. And I guess this is part of the reason that Hawaii also has a remarkably high percentage of its energy from solar panels.
We do. People are pushing to do more and more of it, but it's certainly because essentially we have no hydropower out here or geothermal or anything on that level. So essentially everything is done through fossil fuels that are brought out here and burned, basically. So this would probably be a wonderful spot for you to do some testing and sort of test the whole sort of business end of developing this and getting it into a real world environment. And there is certainly plenty of sunlight around here to give it a good test. So perhaps you should consider this as a interesting field test site. You know?
Oh, definitely. In fact, there's a little subtle point here, which is that how well the system works is also dependent on the properties of the atmosphere in the infrared.
Mm-hmm.
And one of the best places in the world probably for this effect is the top of Mauna Kea. Of course, that's probably the spot where you need the least amount of cooling in Hawaii. But
exactly.
But it's because it's so high in altitude, you can basically send more of your heat out, and less of it gets reflected back by the atmosphere. So this effect, you can do, and incidentally, flight astronomers are up there as well, because you get a clear amount of signal. So it's all tied into the same principle.
Right, yeah. But as you point out, that's probably not the place that needs the cooling, since they do have snow up there, at least part of the year. But certainly here in downtown Honolulu, we get a lot of sun and a lot of heat, particularly in the summer, and so it'd be fun to take a look at this stuff.
Yeah, our research is funded by the U.S. Department of Energy and an agency called ARPA-E, the Advanced Research Projects Agency, Energy. And as part of that, one of our, hopes and goals is definitely to test this kind of system in different regions under different conditions to identify where it might work best and what the performance might be. So I think that's something we're definitely looking forward to doing.
Excellent. It sounds like you have quite a tiger by the tail, as it were, there for this. And what do you see as the sort of the time scale of development for this? Is this something that we'll be seeing in some sort of commercial form in the next few years?
It's difficult to say for a few reasons. My hope is within 3 to 5 years. I think the challenge with any kind of technology that goes on buildings is that the cycle for them is relatively slow. It takes time to validate performance, and as you might expect, anyone who would consider purchasing a system like this wants to see proof that it has worked elsewhere for a while, and so you have to do a lot of kind of pilot studies and testing. But I'm definitely optimistic. I think there's, at least early on, there are, I think, unique niches for this where it can provide a compelling value that should allow us to at least, try and further the development of a lot of the technical challenges that come with converting, a research concept into a product. So I'm certainly optimistic.
Excellent. No, it is very exciting, and it's such an interesting idea. As you point out, there's been a relatively huge amount of work in the sort of underlying research, photovoltaics and solar power, and this sort of the converse has gotten so little attention, and it's wonderful to see as these days of rising global temperatures, the thought that one day you could really begin to dump excess heat out and turn the universe into our great heat sink is a very it gives us hope,
Well, I'm glad to hear you think that.
Excellent. This is super. So, is there anything you'd like to sort of wrap up with in terms of a take-home message from your work that you really want to share with our audience?
Well, my view on this kind of work is at the end of the day, when you've worked on it for a while, you think, wow, this isn't actually at the end of the day that complicated. It's in retrospect, a lot of ideas that can seem kind of counterintuitive and very novel are often quite simple. And in the end of the day, I like to think of this as a relatively simple idea, and simple in a good way, meaning that it's something where a lot of the advances we've made in a basic understanding of light, how nanoscale objects interact with light, can actually make an impact on something that matters to us on an everyday basis, and that's how we use energy. So it personally keeps me motivated and keeps me excited about working on these kinds of concepts, because you're able to tie the basic scientific process, the basic scientific research that is intrinsically interesting to problems that matter to everyone, including myself as a scientist. So I hope this is kind of just an inkling of what is yet to come out of fields such as these.
Well, thank you very much. That was very eloquently put. You've been joining us here on Likeable Science. I'm your host, Ethan Allen. Today I've had the pleasure of the company of Dr. Aaswath Raman from Stanford University. We've been talking about the photonic radiative cooling system that he's developed. Truly amazing, and it looks like probably revolutionizing system with lots of application around the world. Thank you so much for joining me, Aaswath. I've really enjoyed talking with you here. I wish you the very best.
Thank you very much for your time.
Aloha.
Aloha.